Dynamic chemical equilibrium. Not an easy subject to understand. It helps if you can visualize at the submicroscopic, the molecular level, but that's not easy to do either. I'm going to try to give you an analogy that helps to understand this concept. There are plenty of analogies around. Lots of them are simply duds. Lots of them create misconceptions. Mine, different. So what about, do you like my new red board? The characteristics of a reaction mixture in which the reaction is in this condition of dynamic equilibrium are these. It's a closed system, no stuff coming in, no stuff going out. The concentrations of all the species are not changing with time. And as a result of that, the properties like density, like refractive index, are not changing with time. And the reason that we have for this, and we have plenty of evidence, is that there is reaction going in one direction, whatever that means, and in the opposite direction, not only simultaneously, but at equal rates, equal numbers of molecules changing this way and that way. Now this concept of what does it mean, that rates are going in opposite directions and at equal rates. Reactions are going in opposite directions at equal rates is a very, very difficult concept. And I'll try and help with that. Before I do, we need to accept, or at least my way of thinking is going to require us to accept this, that all reactions are competitive process. Nothing ever happens by some reactant throwing away a hydrogen ion or a carboxyl group or an electron. There's fighting between reactants to grab certain parts of molecules or electrons or whatever. And whether the reaction happens or not and how far it happens depends upon the competitiveness of the reactants for whatever's being competed for. Now I'm going to use, just by example today, acid-base reactions, which I can generalise as a species with a hydrogen ion attached to it, reacts with a base, this is the acid, reacts with a base B to form these products, and the products are formed as a result of a transfer, or at least a competition, grabbing of hydrogen ions by the B base, leaving this without hydrogen ions and forming BH. And it's going to be easier to think not about reactants, but who's got the hydrogen ions that are being competed for. Okay, I could have chosen oxidation reduction reactions, which are competitions for electrons. And we get the scale of standard reduction potentials. I can't do it all, I'll just choose acid-base things. And my analogy is this. We're going to have players competing for footballs. Our reaction vessel is a playing field. It's a closed system in the sense that no players, once we've defined our players, no more can come on, no more go off. And our players are AH. There are 200 of players that I'll call A players, each of them carrying a football, which I'll denote as H, that H. And there's 1,000 B players coming onto the playing field. None of them have footballs. The A players and the B players mingle and they compete for these H's, for the footballs. And we have to accept that AH and A are different species. That's a different species from that. Just like acetic acid, the acetate ion, they're different things. Reactant, product. And B and BH are different species. Should we play some games? Let's. I know I've got a lot of writing, a very crowded board. So be it. We're going to have some competitive games between species AH and B for the H, the footballs that A's carry. And there'll be 200 AH come onto the ground and 1,000 B players come onto the ground. What will happen? Who will win the H's, the footballs? What do you think? Yeah, if you are answering, it depends, then you're giving probably the right answer for every question in chemistry. It depends. But to understand the chemistry, you need an answer to it depends upon what. And I hope that that will become clear. So let's play some games. First one, 200 of those and 1,000 of those come on. And the B's, the B players are so gentle, so delicate, so loving of all mankind. They don't want to grab footballs from the A players. They want to sit on the ground and admire the A players holding their footballs. And so be it. And at the end of time, there's no change to anything. There are still 200 of them. There are still 1,000 of them, and there's been no transfer, no fighting, no winning of footballs by the B team. So we're talking about relative competitive ability of A's and B's. In this case, the analogy corresponds with what we would call in chemistry no reaction. Nothing happened. Let's go to another extreme case. On come 1,000 B players, and every one of them's a ninja warrior, and they are hungry for footballs. So we have 200 of these, 1,000 ninja warriors. What do you think happens? Yeah, in a flash, all the footballs are grabbed by the ninja warriors, the B's. And what are we left with? There's no AH species left. All the H's have been grabbed to form BH. There's 200 A's because H has been taken from the 200 A players, and there's 800 residual B's. There'd be more reaction if there was more of AH. I hope you're thinking limiting reagents. Digression. We call that a complete reaction. And that'd be fairly characteristic of acid plus base goes completely. Acetic acid, hydroxide ions will go entirely to acetate ions and water. These are ninja warriors in the acid-base sense. Okay, let's go to somewhere in between. Let's have B's, let's have A's more competitive than up here. A bit ninja-ish. We mingle and they fight for the balls, the 200 H's. They fight. And I've got pictures taken by a drone, and I look at the playing field after a little time, and I see that there's 196 AH's, there's 4 A's, 996 B's and 4 BH's. What do I deduce from that? I deduce that 4 of those 200 footballs have been grabbed by B's. So now the B's are not all that competitive with the A's. I've only managed to grab 4 of them. And I look again several seconds later. Still, there's only 4 BH's. and I look again. So it looks like nothing's happening. The reaction's finished. Hang on. The 4 B's that have got H's now are not the same 4 B's as had them before. Wow. I look again. This next photograph taken a second later. Again, there's 4 BH's, but a different 4. Again, what's going on? I play a video now and I look down onto this playing field, and I see that over here on this playing field, a few A's are grabbing a football from a B, and over there a B is grabbing a football from an A, and these transfers, these grabbings are happening all over the place. And it happens, when I check this, every second 14 H's are grabbed and go that way, and 14 go that way, meaning that the concentration, the number of that and that stay the same, not because nothing's happening, but because the transfer of protons is going that way, the same number per second as going that way. This state of balance, equilibrium, and dynamic, there's stuff happening. So sometimes it's easier to think about dynamic chemical equilibrium by thinking not so much about the reactants, but by thinking about the stuff, the thing that's being fought for. So this is a situation where B's aren't able to grab too many of the hydrogen ions, the footballs, I beg your pardon. It's something like acetic acid in water. Around about 1%, depending upon the concentration, ionizes. About 1% of those protons are grabbed by waters to do that. Something like the situation we've got here. Okay. Let's have a fourth game. And after a little time, we look at the photographs taken by the drones, and we've now got 50 AHs left. So there's got to be 150 A's, because 150 protons must have been removed from the 200, 850 B's and 150 BHs. And that stays the same. But again, when I look, they're not the same players have got the footballs. Some A's are grabbing footballs, some B's are grabbing footballs from A's. This process is going on, the fighting, the competition, excuse me, the transfers backwards and forwards. And now I can see from the video that every second 37 go that way per second and 37 go that way per second. But they're different players possess the footballs at any one moment. Dynamic, simultaneous transfer or competing for and grabbing of the H's, and it's the relative competitiveness of the species A and B, which is different there, from there, from there, from there, that governs how far the concentrations or the numbers of players has to be before the rate of grabbing this way becomes the same as the rate of grabbing that way, and we reach the state of chemical equilibrium. So, from these I hope it's clear. Firstly, this condition of dynamic transfer, competitive transfer, depends upon the competitiveness, the competing ability of the reactant species. Just one more idea. In game 5, we have the same participants as up here, but instead of 1,000 of B, we only mix 400 of B. Now what do you think will happen? How many protons will be grabbed by the B team at the point of equilibrium? I'll leave that with you. I just want to bring the second point. Not only is competitiveness of the species determine where the point of equilibrium is, but so too does the relative number or the relative concentrations of the participants in this reaction vessel, playing field, determine that point of equilibrium. Think about that. And I hope that that helps to form an idea of what's meant by the reaction is proceeding in both directions simultaneously and at the same rate. Think about it as transfer of the competed species is happening in both directions and at the same rate in terms of numbers per second or concentration per second.